Okay, welcome everybody to the second day of Virus Bulletin. This is the second presentation in the red track. Today we're going to have a presentation on bootkits, past, present, and future. Our presenters today will be Eugene Rodionov and Aleksandr Matrosov. Please join me in welcoming them to the stage.
Good morning, everyone. So we can start. As the title of this presentation suggests, today we're going to be talking about bootkits. We'll consider how this kind of malware evolved over the recent years and discuss the future attacks vectors against unified extensible firmware interface systems, which are gaining popularity nowadays. This is a joint presentation of three researchers. Unfortunately, one of them, David Harley, was not able to make it here. My name is Eugene Rodionov, and I'm a specialized researcher with the ESET. In the last few years, I've been doing in-depth analysis on complex threats, and the bootkits is a significant part of the complex threats I came through during the last few years. I'll let Aleksandr Matrosov to introduce himself.
I'm Aleksandr Matrosov. Thank you for coming for this morning session. I'm working for Intel Advanced Threat Research Team. It's a new team at Intel starting in the beginning of this year, but we already made in use with Mozilla NSS library yesterday. I highly recommend to update your browser, Firefox and Chrome.
All right, so this is the brief overview of this presentation. It consists of several parts, so we'll start with an overview, a historical overview on the bootkits, how they evolved over the recent years. We'll consider bootkits seen in the wild, as well as their proof of concept implementations. And we'll speak about the classification of their legacy-based bootkits, which we came across. Then we'll move to discussing the attack vectors, which is a kind of for present and future against the unified extensible firmware interface. We'll touch secure boot implementation on Windows 8 and the ways one can bypass this security feature. And as well, we will discuss and present software which is used for forensic analysis against the bootkits. So this is their ESET hidden FS reader and Intel chipset framework. So I'm going to start with the slide which depicts the history of the modern bootkits, or modern history of bootkits. I hope everyone here can clearly see the image. So on top of the slide, you can see the bootkits seen in the wild, while at the bottom, these are the proof of concept implementations. I want to bring the attention of the audience to this period, which is marked as the Microsoft 64-bit platform gains popularity. We can see that actually most of the bootkits, as well as their seen in the wild and proof of concept, appeared at this time. So this is the time when the modern bootkits were flourishing. And the main reason for that is their security enhancements in the Windows 64-bit platform, specifically Microsoft kernel-mode sign-in policy, which prevented loading unauthorized kernel-mode modules. This pushed the rootkit developers to adopt a new vector, specifically bootkit vector, to be able to circumvent this security enhancement. So this is a kind of past and present. The other period of time we can describe as the unified extensible firmware interface platforms gain popularity and secure boot is implemented in Windows 8, which was released in the end of 2013. So this is an important milestone for a kind of newer bootkit era, because this is a new platform which is different to their legacy-based systems. And we can see that there is here a first proof of concept bootkit targeting your unified extensible firmware interface by work labs. So this slide brings us to our discussion what's the difference between the legacy-based systems and the new unified extensible firmware interface, and why the Bootkit targeting the new platforms are different to the legacy ones. So first of all, there is no more MBR and VBR in the unified extensible firmware interface platform. So for those who are not familiar, MBR stands for master boot record, and VBR is the volume boot record. IPL is initial program loader. So these components, which are shown here, disappear at the unified extensible firmware interface. And that's why the malware targeting the legacy-based system is not able to infect the new systems. The other difference is the hard drive partitioning is rather different. The GPT or partitioning team is used in the UEFI systems. And secure boot technology is implemented in Windows 8. So this is a part of UEFI specification which enforces their authentication and integrity verification of their boot modules involved in the boot process. So this technology is designed to eradicate the Bootkit threats on the new systems. So the previous slide actually splits the presentation in two parts. So in the first part of the presentation, I'm going to go through the Bootkits targeting legacy biases, and in the second part of the presentation, Aleksandr Matrosov is going to concentrate on their UEFI attack strategies and the ways to bypass secure boot. So let's start with the legacy bias bootkits. On this slide, you can see here the generalized picture of the boot process on this system. So there is some bias initialization which takes place in the first, and here is where MBR kicks in, which it receives control and handles the boot process. These are the components which are frequently targeted by the legacy bias bootkits. So it is in some sort of tampering with this code or replacement with the malicious ones. And here is the classification of their MBR and VBR bootkits. So generally, they can be split in two parts. The first one involves modification of the MBR, where the second big group involves modification, tampering with VBR or IPL. The first group, in turn, may be split in two subgroups. The first one involves MBR code modification. The other one is partition table modification. So MBR is the data structure with the code which consists of two parts. The first part is the MBR code which handles the boot process. And the second part is the partition table which defines the partitioning of your hard drive. So the TDL4 is the representative of the first group when it just modifies the MBR code, but it leaves your partition table untouched. Almask, in turn, is different. It doesn't touch MBR code, but it modifies partition table. In fact, it creates a new partition table entry in the partition table, marks it as an active one, and this is how it receives control at the next boot up of the system. The next group, VBR and APL, is different and a little bit more complicated than the previous one in terms of their detection and remediation. It can be split in turn in two parts. The first one is the IPL code modification, and as we will see on the next slide here, this is how the Rovnix infects the systems. And the other one, which is the way more interesting, which was implemented in the Gapz Bootkit, it involves bias parameter block modification. So let's see the Rovnix infection strategy. On this slide, there is here a picture of the layout of the hard drive before and after infection. We can see that the bootstrap code, in fact, this is an IPL, which gets infected in the following way. The malware just compresses it and appends to the malicious code. And this is how it receives control at the next system startup. You can get more information on this threat and this infection vector at this reference. The second type of VBR IPL infection strategies is the modification of the bias parameter block. And this is your infection vector is adopted in the Gapz Bootkit. So this is very interesting because the infection results only in modification of only 4 bytes of the VBR. So on this slide you can see the layout of the VBR. It starts with the first 3 bytes of jump instruction, then there is a VBR code which takes over. And this structure is the bias parameter block, which describes the parameters of the NTFS volume. So this is a file system specific structure. Here is how it looks like for NTFS file system, and the highlighted you can see the hidden sectors field. This is actually the target, only 4 bytes which the Gapz modifies. So this is just in hex. These are the 4 bytes which are patched. The rest of the VBR remains unmodified. So the meaning of the number of hidden sectors in the NTFS system that specifies an offset to the initial program loader, which is used at the system startup. So this is on the clean system. The number of hidden sectors points to the correct location of the IPL. On the infected system, the modified number, the value of the hidden sectors point to somewhere else. This is where the Bootkit code is located, while the rest of the VBR and MBR code remains untouched, and it's actually quite difficult to spot this infection in the wild, because the 4 bytes which Gapz is modifying, they may be different on different systems, and for instance, you cannot create a static signature that will allow you to easily spot this threat in the wild. One needs to take a more deeper approach to be able to find infection on the machine. So this slide summarizes the features of the most widely spread bootkits seen in the wild. So such features are MBR, if it's MBR or VBR type of modification, if there is any kind of hidden storage implemented by the Bootkit threads, because since the Bootkit threads take over before the operating system is initialized, and therefore they cannot use the file system provided by the operating system. So in most of the cases, they implement their own custom hidden storage. As we can see here, it may be either a FAT32 system or some custom implementations, which is generally encrypted, sometimes compressed. And another interesting feature is the custom implementation of TCP IP stack to communicate to CNC server. So this is done to bypass personal firewalls and network detection tools which are installed locally on the infected machine, because the malware doesn't utilize their operating system TCP IP stack, which is usually hooked by this security software, but implements its own. And we can see that the Gapz and the latest modification of Rovnix use this feature. So to be able to do forensic analysis, to be able to extract the information from the hidden storages, in the course of our research, we implemented a hiddenfs reader as a forensic tool, which allows to dump contents of the hidden storages. So for instance, on this image, we can see that it's dumping the contents of the Gapz VBR file system, and all the configuration files and the modules and the payload. And here is the list of all the malware which is supported by this tool. So this is the small conclusion of this part, and I'm passing the word to Aleksandr Matrosov, who will guide you through the Unified Extensible Firmware Interface attacks.
Then world moved to UEFI. We have 20 more slides for the next 10 minutes, and some slides I will be going quickly. So, after using UEFI, it's not mean legacy BIOS bootkits not worked. It's not worked with some new operating systems which support secure boot. But if you use some, as example, Windows 7 incorporated still used, it's possible to boot with legacy MBR, VBR support with new UEFI BIOSes. So it's the first brick, some last interesting threads overview. Chernobyl, first brick for BIOSes, Mabromi, first BIOS kit abusing BIOS update process. Okay, it's high-level picture for UEFI firmware boot process. We're starting from CPU reset vector and going to the next steps. Most interesting is driver execution for Dixit drivers. It's possible to abuse by malicious drivers. Also, it's possible to modify some boot OS loaders and on these steps. Okay. On this picture, you can see the hardware level, system firmware level, UEFI driver and core, and some components of UEFI loaders, which booting the operating system. And the first vector of attack is abusing bootloader on this level. And we currently know 3 ways to do this. The first one is some old technique with replacing boot manager directly. And also interesting is replacing fallback bootloader directly into the file system. It's already presented in the last year by Sebastian from Quark's lab. And sources of this BIOS kit, UEFI bootkit, it's available on the GitHub. And the last one, it's adding new bootloader, also directly in file system. It's really easy to detect by antiviruses because it's possible to recognize into the file system on operating system level. The next one is if malware abused operating system and install malicious Dixit driver, it's stored in special storage which stored in fixed drive, and it's not embedded in the volume, but it's possible to boot before operating system if provided modification by malware for driver order in UEFI variables. Also interesting, it's abusing UEFI option ROM. This way presented by Snare in Black Hat 2012 for MacBooks and macOS operating system with proof of concept and live demo. It's a really interesting way, but so complex, and I don't see some public proof of concept for this technique. And the last one, it's replacing directly bootloaders, WinLoad UEFI, WinResume UEFI, and punch and GUID partition table. Punch and GUID partition table, it looks like a callback to the legacy BIOS threads for MBR, VBR, because directly working with some configuration for partitions. Okay, if we compromised by malware all those levels, we can abusing OS on the early booting steps. What about secure boot? Of course, on some new operating system, Windows 8, Windows 8.1, using secure boot, and it's really interesting and good technology for against bootkits, but has some information about attacks on secure boot too. Okay, looking on this scheme, and BIOS updates go directly into firmware level, and if abused the UEFI, we can modify, we can break chain of trust and booting operating system without support of secure boot. It looks like this, exploit going from operating system level directly to abusing firmware, and on the next steps, it's breaking chain of trust. The first public Windows 8 secure boot bypass presented in the last Black Hat in 2013 by my team. And in this year, Mitra presented also a really interesting technique for bypassing secure boot on Windows 8.1. More information you can find on the paper. It's just demonstration in the last year for bypass secure boot on the live platform. In this year, we presenting Rodionov the summary of attacks against BIOS and secure boot. On this figure, you can see 8 different ways to compromise system firmware and BIOS on UEFI, with UEFI support. And all exploits demonstrated on DEF CON, discussed on DEF CON, and we provide some live demo for bypassing secure boot too. What is the main problem with BIOS vendors? It's a lot of BIOS vendors, but don't have a unified procedure for update the BIOSes. And each vendor going to update by different rules. In the beginning of this year, was presenting really interesting system, Subzero by Teddy Reed. It's the special crawler which download BIOS updates and provide some simple patch diff technique. And this technique really simple to recognize 1 days. And it looks like BIOS exploits possible to use not just for targeted attacks. It's not expensive to just run a crawler and recognize some 1 days, because sometimes the patch, it's really simple, just modify one variable or removed some dwarfs. Okay, the next part of my presentation, I will be discussing the ChipSec. It's platform for assessment, for platform security assessment. And it's open source, and on this week we released 5 new models and also support a new version of Linux driver for better support this platform. It's possible to run from Windows operating system, Linux, and also directly from UEFI shell. It's architecture. All functionality of ChipSec working from Python, and we have some hardware abstraction layer which working directly with hardware by driver. And all this functionality you can use from Python. It's really, really useful tool. Also, today afternoon, Mitra will be presenting information about Copernicus. It's the second tool for UEFI security assessment. Really interesting, and I highly recommend to come. Okay. It's some information about models. It's the conference when these techniques was presented from ChipSec. ChipSec possible to use for BIOS forensics and firmware forensics. A lot of information covering from configuration chipsec has decoders for UEFI and some BIOSes, and you can unpack all information for forensic process. Also, chipsec have software support to dump from spy flash firmware, but I highly recommend to forensics use some hardware tools, because if the platform abused by malware, you don't have a guarantee. If you get a firmware dump by software, it's not modified by malware in the dumping process. And it's some really cheap tool with Bus Pirate, good fat, just $30. But you need documentation by spy flash chip for recognize right pins and not damage a chip. And DDProc, it's a more expensive tool, but have really good software with automated recognizers for most known chips used by vendors. Not only for BIOS, for a lot of things. Okay, how many time we have?
We have about 3.5 minutes.
Okay. We have some demonstration, and we take bad BIOS image which shared by Dragos in internet and try to make some simple forensic procedure. Okay. So. Run a demo, but I don't see the button. Okay. So it's infected image. It's update. It's original image going for BIOS update this version and downloaded from vendor side. We run a chipsec. Chipsec support most common configurations for the platform for decode. And we run decode for infected and for original one images. And get all variables and structure and so on. It's after dump structure of directories, a lot of stuff. Okay. And after, we run recursive diff for each directory with original one to infected. Okay, run a diff. So, we have some differences, but if you look, it's differences in VRAM, and BIOS update don't have in VRAM. In VRAM, it's initialized into the platform. And we don't find something interesting in the bad BIOS and just used this image for get your attention. Okay, back to presentation. So, if we conclude our talk, the legacy BIOSes for for operating system which not supported UEFI and secure boot, it still worked. But new operating system have also some techniques for bypassing security technologies as secure boot. And we don't have a lot of time, and going to the next slide. In the next year, I am Eugene, and Eugene, we presenting advanced malware analysis book. We're working with No Starch Press, and highly recommend to get this book. Thank you for your attention.
Thank you, Eugene and Aleksandr. Unfortunately, we don't have any time for questions. So again, everyone join me in thanking them for their wonderful presentation.
Thank you.